We discuss here the deterministic logarithmic completeness in the distributed sleeping model, written by Leonid Barenboim and Sadek Maimon. A presentation of the results of the paper and the technique we showed for all decidable problems in this model. The sleeping model is a distributed setting model, in fact, where in each round the vertices can be in one of two states. One is the awake state, where the vertex can perform any task we wish in the distributed setting, receiving, sending messages, and internal computations. Those requires energy. And in the sleep state, it is inactive, cannot do anything of those things, but it preserves the energy, and thus we do not count it towards the cost of the algorithm for the specific problem in question. The performance is considered as the maximum number of awake rounds among all vertices of the graphs. That is to say, for each vertex there's a number of awake rounds, and we consider the performance of the algorithm to be the maximum among all those numbers. The definition of this model was first discussed in a paper of Katraji, Gmir, and Pandurajman in POTSI 20. Their result was a randomized algorithm for a maximal independent set. In this setting, the sleeping model with worse awake time of O log n. They did achieve a constant time algorithm randomized for with high probability, but the average mean time was still O log n. In our scheme, we devise a certain structure with which we prove that we can solve any decidable problem in the sleeping model in constant time. This structure is called the distributed layer tree. Now, the algorithm we devise is actually constructing this structure, and we show that it takes O log n time, deterministic awake time, and not only that, we also prove that it cannot be improved. The construction of the DLT itself requires omega log n deterministic awake time in the sleeping model, and therefore any decidable problem. If we take any decidable problem, it has the lower bound of omega log n. Thus, the class itself has that completeness, and this is the main result, the core result of our paper. We will see now what is a DLT first. It is actually simply a spanning tree, a directed spanning tree, which has a labeling. Each vertex has a labeling, and we can say that each vertex has a label greater than the label of its parent. Not only that, each vertex knows the label of its parent, which sounds quite easy to achieve in a normal distributed setting, but not in the sleeping model, where it is not necessarily easy to pass information from one node to another, because we need them both to be awake at the same time for the message to transfer. How does a DLT help us at all? Why should we bother with it? Well, if we have a DLT, we can solve any decidable problem in constant deterministic awake time. What we do is we perform a converge cast to the root of the DLT. The root solves the given problem internally for the entire graph, and then broadcasts the solution to all the nodes. Thus, all nodes know the solution and can decide what their part of the solution is. How does a cast help us? Well, if we have a DLT, both converges and broadcast takes exactly 2 awake rounds using a DLT. I do remind you that It means that each vertex will be awake at most 2 rounds during the procedure. So for example, for a broadcast, this vertex is awake at around LV and LPV. I remind you that V knows the label of its parent. So if the asterisk in this example is the information that needs to be broadcast throughout the graph, and this is the DLT, the children of the root know the label of the root. Thus, they can be awake at the same time as the root, because the root is awake at its own label, and also the children are awake at the same round. So the root can broadcast, send messages across the edges, and we know that the message comes across to the children. Now each child has its own labeling, and the grandchildren now can be awake at the proper time. Now in this example, it seems like all the children in the second level of the tree are awake at the same round. It's just for an example. It's not really necessarily the same round. They can have different rounds, but what's important is that the children of this in the third level are awake in the proper rounds according to the knowledge they have to the labeling of their respective parents. So the information can propagate down the tree, and again it can propagate down to the fourth level and so forth. And if we can see the example, we can see, for example, that the second level of the tree here are colored blue only 2 rounds throughout the algorithm. And so this is true for any level, and a broadcast it indeed takes only 2 awake rounds using the DLT. A converge cast can also be used in the same way. All we need is really a number and tag, which is larger than the size of the labeling. And just by subtracting the labeling from and tag, we reverse the order of the labeling, and we can propagate up the tree instead of down the tree. So also Converge Cast in the same way takes 2 awake rounds. So we can see the power that the DLT gives us for propagating information up and down its structure. All we need really is to construct the DLT in the sleeping model, which is the challenge. We do this by progressing in O log n connection phase, and each phase has 2 stages. The first stage is where each DLT, existing DLT, we can look at a vertex as a trivial singleton of a DLT. Each DLT searches for an outgoing edge to another DLT, T tag, such that the labeling of T tag is smaller than the labeling of T. So in this case, T would like to connect to T tag and be a subtree of T tag now through the edge UW. How does it happen? U knows that T tag is has a smaller label, because this is easily achieved by having all the vertices of a tree knowing the label of the tree, and you can then send the edge up to the root. The root can decide, all right, T is going to connect to T tag. It found a neighboring DLT to connect to, and now it sends the information of a new labeling to the entirety of T by simply saying the distance of U from W is 0, actually 1, but we can subtract 1, it doesn't really matter. And we are relabeling T such that the labeling inside the T is still upholding the rules and the properties that we are expecting from a DLT, and yet W will have a larger, a smaller label than T, simply by saying that the label of use is a pair, which is the ID of W, comma 0. The ID of this vertex is now the ID of T tag, the LW, comma 1. So we guarantee that the labeling of this vertex is larger than this, and obviously by relabeling this properly, we make sure that all the IDs in this tree are still upholding the properties of a DLT, but also the connection between those two connected components also uphold the properties of a DLT. So now those two blobs are one single DLT. The problem here is that when T chooses a neighbor, it might not find a neighbor which has a smaller label. Maybe T is a local minima. So thus we perform a second step. If we have T1 and T2, which are local minima, and what they simply do are they arbitrarily can choose a neighboring connected component, some C. And what we do, we wake all the graph in a single round. The entire graph is wakened up, so all the information can pass. T1 is informing C that it wants to choose it as a connected component, and T2 wants to do it as well. Now C knows the structure of T1, it knows the structure of T2. So what happened is by doing a converge inside C, the root of C can relabel C, T1, and T2. All those trees are recalculated as a single DLT with a proper labeling. And this needs to be propagated. It propagates down C. We do another wake up to the entire graph, and T1 and T2 receives this new labeling, and they actually become part of C now. They became one DLT along with C. So all three blobs are now a legit DLT. Why did we do all this? Well, the reason is quite simple. We made sure that there, in each connection phase, each connected component is paired with at least one other DLT, other connected component. So obviously we only need at most O log n phases to finish connecting the entirety of the graph. So after O log n rounds, we make sure we have one spanning graph that spans the entire nodes of the graphs, and each connection phase in fact takes a constant number of awake rounds. These are the numbers we can see on the steps themselves. You can see that each step requires a constant number of awake rounds. So in total, our algorithm of constructing a DLT in the awake takes O log n deterministic awake time to construct. And although being too vast to bring into this presentation, we in the paper in fact proved that this cannot be improved. This decidable problem of constructing a DLT, it by itself requires at least omega log n, and thus the entirety class of the decidable problems has this lower bound, and it's in fact a tight bound. This actually proves the completeness of the decidable problems in the sleeping model. The second result we show in the paper is about the class of O local problems. We define this class of problems in the paper, and it is defined in a way such that if we have a problem in which we are given an acyclic orientation on the edges and some problem P, the problem P should be solvable by having each vertex awaiting the decision of all of its parents according to this orientation, and then it can decide by itself what each should have as a solution. So for example, MIS is a good example for an O-local problem, because once my parents decided if they're in the independent set or not, I can decide if I'm adding myself to the independent set or not. So MIS is obviously a local problem. Also, coloring is an local problem. And we give a deterministic algorithm for solving any O-local problem in O log delta plus log star n awake time, which is better than our algorithm for any decidable problem. Obviously, it's a smaller class, so a better result. The concept is that given some coloring of size d, we build a binary tree inside each vertex, and this binary tree looks exactly the same in all the vertices. And according to this tree, the vertices are awake or sleep and can receive and send messages to the neighbors. We simply chose to use Lineal's algorithm for O delta squared coloring in O log star and clock rounds for the coloring stage, but any coloring algorithm will really do, but it will set the additive term in the performance of the algorithm. Once we are giving a coloring, our algorithm runs in O log delta time. And so given a decoloring, we are building a full binary sorted tree such that the decolors are mapped to the numbers appearing in the leaves of the tree. So if we look at the tree, we can say that 1 is mapped to the first color, 3 is mapped to the second color, 5 is mapped to the third color, and so on and so forth. And above that, we have the binary tree itself. So how does it help us? So the way it helps us is that each vertex is now awakes itself at the number of rounds equal exactly to the number appearing in the root between the leaf of its color up the tree to the root. So for example, the vertex with the color 13, which is mapped to the leaf 13, will be awake at round 13, 14, 12, and 8. This will be awake at 9, 10, 12, and 8. So how does it help us? If you pay attention, each color in the leaves, if my color is 13, for example, all my parents must appear before me to the left side of the tree. So we must have some shared number in which we are awake at. Obviously, everybody is awake at the number of the root, but the question is, at this point, did all my parents already decided what they need to do? Well, the answer is yes, because this is a sorted binary tree. Everyone to the left of the root already made their decision, so everyone to the right of the root can use those decisions to make their own decisions, which is exactly the property of the class O-local problems. So if we take this as an example, 13 needs to make a decision. It awakes at 14. At 14, it sends the decisions to 15, and 15 knows to receive it because 15 is awake. It awakes at 12. So at 12, it needs to receive information. So it needs to receive information from all the parents coming from before him. It can receive from number 9 and number 11. At 8, it can receive from 1, 3, 5, and 7. At 13, it makes the decision. At 14, it sends the decision to 15. And thus 15 can make the decision if 13 is indeed a parent. So we make sure that by awaking a vertex to in a number of awake rounds equal to the depth of the binary tree, any O local problem can be solved. And a binary tree has only O log delta depth, and thus it is the performance of the algorithm. And any problem can be solved in O log delta plus log star n awake rounds, where I remind you, if we have some randomized algorithm for O1 coloring in O1 time with delta coloring or all delta coloring or even some polynomial of delta, then our algorithm is immediately becomes a black box and to a randomized algorithm for all local problems in O log delta time. This concludes this presentation. I thank you very much.